Okay, guys, I wanted to do a series of videos here on the NMR chapter. We'll talk about magnetic resonance, and in this first topic, we'll look at some of the general ideas behind NMR. As you know, nuclei have an intrinsic spin angular momentum, just like electrons, and commonly for nuclei, the spin quantum numbers are represented by capital I and an M sub I. And these are analogous to the quantum numbers S and M sub S that we use for electrons, and they work in pretty much the same way. The length of the spin angular momentum is given by this expression here in terms of the quantum number I. And then the z component of the spin angular momentum is given by m sub I times h bar. And the value of m sub I runs from negative I to plus I. So this is perfectly analogous to what we had for electrons. The spin states are degenerate, at least in the absence of a magnetic field, and the degeneracy is 2I plus 1. One difference between electrons and nuclei, for electrons, the spin quantum number S is equal to 1/2 for every electron. All electrons are the same. Of course, we have different nuclei, and different nuclei, depending on the number of protons and neutrons they have, can take on different values for the spin quantum number. And so I've listed a few here. The most important ones to chemists really are protons and carbon-13 isotopes. These are both spin 1/2 particles, just like electrons. And so there's an up state and a down state corresponding to m sub I equal to plus or minus 1/2. But other nuclei have different values for the spin. For example, the nitrogen-14 has a spin quantum number of 1. And so there are 3 possible values for m sub I. A carbon-12 isotope, on the other hand, has a spin quantum number of 0, and so there's only one m sub I value for carbon-12. This table here lists values of I that you would expect for isotopes with different parity as far as the number of protons and neutrons that they have. And so I think for the carbon-13, we would have an even number of protons but an odd number of neutrons, giving you half integer values of spin. However, for the proton, you would have an odd number of protons and 0 neutrons. You would also get a half integer spin there. Well, the spin angular momentum is associated with a magnetic moment. That's represented by the operator mu here. Mu is related to the spin angular momentum, and the proportionality factor here, gamma sub n, is called the magnetogyric ratio for that particular nuclei. So the value of gamma n depends on what nucleus you're talking about. And it can take on commonly positive values, but also negative values. And when gamma is positive, that means that the magnetic moment points in the same direction as the spin angular momentum. If gamma is negative, then the two are antiparallel to one another. Well, that magnetic moment can couple to an external magnetic field. So the idea here is you put your nuclei in a magnetic field. There's a coupling between the nuclei's magnetic moment and the magnetic field, and that's illustrated by this Hamiltonian here. Okay, so there's a dot product involved. These are both vector quantities, right? The magnetic field vector points in a certain direction. The magnetic moment points in a certain direction. And if we make the assumption, which is perfectly fine, that the magnetic field is aligned with the z-axis, then the coupling occurs between the z component of the magnetic moment and the magnetic field. So B naught here is the strength of the magnetic field in the z direction, and mu z is the z component of the nuclei's magnetic moment. And based on this relationship up here, mu z, as you would expect, is related to the z component of the spin angular momentum. So this is the coupling term between the magnetic field and the nuclei's magnetic moment. You can calculate the energy levels. The energy levels of this Hamiltonian will be identical, or the states would be identical to the eigenstates of the z component of the spin angular momentum. And so we wind up with these eigenvalues here, where the action of Iz gives us the quantum number m sub I times h bar. And so what we see is that the energies of the different spin states are split by the magnetic field. So with no magnetic field on there, the energies are all the same. They're all degenerate for every value of m sub I. But when you turn on a magnetic field, then the values are split according to the value of m sub I. So in this case, let's assume that gamma is a positive number. For all of the positive values of m sub I that you have, the energies will be lowered. For the negative values of m sub I, the energies will be raised. So you get a splitting. On this slide, we're doing a little bit of unit play here, which is discussed in the textbook, but I just wanted to go through it a little bit. What we're doing here is we are coming up with an alternative formula for the energy levels using different quantities. So we introduce the quantity mu n, which is called the nuclear magneton. It depends upon the fundamental charge, h bar, and this is the mass of the proton. So this is a constant. It takes on this value. It has units of joules per Tesla. Recall that Tesla is the unit of magnetic field. We introduce another parameter here. This is not the degeneracy. This is called the nuclear G factor. Okay, so each nucleus will have its own nuclear G factor. It depends on the magneto-gyric ratio of that nucleus times h bar divided by the nuclear magneton. And if you start substituting these things into this equation here and rearranging, you can come up with this alternate expression for the energy levels. And you might have to use that formula, or you might have to use this formula, depending upon the problem that you encounter in the homework. So I just wanted to point out there the difference between this equation and that equation are the constants that you're using, but they are equivalent to one another. Okay, so what we'll do is we'll consider a spin 1/2 nucleus. So a spin 1/2 nucleus has two states. They have a spin up state and a spin down state. The spin down state has a higher energy than the spin up state when the magneto-gyric ratio is positive. And so what we'll do is we'll calculate the difference in energy between the spin down state and the spin up state. And so we just plug in to this expression the formula for the energy levels, and you wind up with this expression here, expressed in terms of the magneto-gyric ratio, or you can express it in terms of the nuclear G factor, if you like. They're both equivalent to one another. Well, now that we have two split energy levels, you could imagine doing a spectroscopic experiment where you bombard the system with radiation, and you could cause the nuclear state to flip from one state to another, say from the up state to the down state. And so what we're doing here is we're calculating the resonance condition for such a transition. So the photon energy involved is equal to that delta E. This is the resonance condition. And then just substituting in that value, we can solve for the absorption frequency. So this is the so-called NMR frequency for your nuclei. And it depends upon the magneto-gyric ratio and the field strength, the magnetic field strength. This is also called the Larmor precession frequency. Here's a diagram illustrating the splitting. So when you have no magnetic field, the two degenerate spin states have the same energy by definition. But when you turn on the magnetic field, for our particular nucleus, the spin up state goes down in energy, and the spin up state, the spin up state goes down in energy, and the spin down state goes up in energy. And this energy difference leads to nuclear transitions, which are possible, spin transitions, which are possible, and the delta E is related to the frequency involved in causing that transition to occur. This diagram is meant to illustrate the NMR frequency. You can think of the magnetic moment of the molecule as spinning around on a cone, okay? And for a given magnetic field, it has a particular frequency. And so this, in a given magnetic field, the nuclear magnetic moment is spinning around. And what you need to do is to find the frequency of radiation whose frequency of oscillation in the magnetic field of the radiation matches the NMR frequency of this nuclear magnetic moment. And when that occurs, we say that you have a resonance. And that will cause a nuclear spin to flip. In this calculation, we're just calculating the NMR frequency for a proton in a typical 12 Tesla magnetic field. So this would be a typical magnetic field strength for an NMR spectrometer. You need to look up the magnetogyric ratio for the proton, multiply by the field strength, divide by 2 pi, and that gives you the frequency, which you will find occurs in the radio range of the EM spectrum. So NMR spectrometers typically use radio frequencies. This slide here kind of just lists the different components that you're going to find in the NMR spectrometer. So you're going to be using a superconducting magnet, typically with the field strength of 10, 12 Tesla or greater. In order to make the magnet superconducting, you need to be operating at cryogenic temperatures, at least for the magnet. And this typically requires liquid helium at about 4 Kelvin. The benefit of using a superconducting magnet is that it gives you a stable field that's very strong, and if you just keep it cool, then you don't have to apply any external power to keep the magnetic field on. Because at these field strengths, the absorption frequencies occur in the radio range, you need to have you need to be able to generate radio waves and then also detect them. Most commonly, we run liquid samples in the NMR. You can have solid state samples, but that's a little bit trickier. Here is a diagram, just pictorial diagram. So you have some superconducting magnet. There's a little space for you to pop down a liquid sample in a test tube that kind of spins around inside the magnet, and then you bombard the sample with radio waves, and then you can detect the radio waves coming out and determine where the absorptions occurred. Well, in this slide, we're discussing the just some general features about NMR spectral intensities. And so the intensity of a resonance is proportional to the rate at which the radio waves are absorbed times the energy or frequency of the photon. And so this is a population difference between the up state and the down state. Okay, so that's that difference is proportional to the rate of absorption times the frequency of the spectrometer. So you plug in this result, which comes from the Boltzmann distribution. We'll talk about that in the next chapter. And then you plug in the frequency, the NMR frequency that we just looked at, and you get this expression here. And what you find is that the intensity of the resonance is proportional to the magnetic field strength squared. So the stronger the magnetic field you're using, the stronger the intensity of the resonance that you want to detect. Okay, so it's good to use strong fields. It's also proportional to the magnetogyric ratio of the nucleus. So nuclei that have a larger ratio will give you stronger intensity in your NMR spectrum. It's also inversely proportional to temperature. That comes from the Boltzmann factor. One thing to note is that these population differences between the upstate and the downstate are typically very, very small, which means that in order to detect these resonances, your NMR spectrometer needs to be very sensitive to small amplitude, to low intensity radiation, and that's the purpose of this preamplifier here that comes in before the receiver. You need to amplify the signal in order to detect it. Well, this illustration here just illustrates what I've stated. They want you to calculate the population difference. Supposing that you had 1 million protons and the nuclear field, or the magnetic field, was 10 Tesla at 20 degrees Celsius. So they just want you to calculate this quantity. And so out of 1 million nuclei, there's a difference in population of about 35 nuclei. Okay, so that's what you're trying to detect, 35 out of 1 million, which is low, right? So that's why your NMR spectrometers need to be quite sensitive. Well, I'm going to go ahead and stop this video right here.